Okay, so any vector on the board can be expressed as a multiple of v1 and v2. And now we have the statement that any vector in space could be represented by a vector on the board if we just tilt the board right and position it correctly. So if we have a plane in space, a plane like here, okay? This plane, I take this board, I tilt it about like this, and now I've got that plane. And the board represents a part of that plane, and extending the board out to infinity in all directions represents the whole plane. So any plane in space can be represented by the board if we orient it right, meaning any plane in the space has the property that if I tilt the board right, the v1 and v2 vectors that we get that are now no longer in this vertical plane, but v1's off this way and v2's out this way, those two vectors can be, we can combine multiples of those two vectors just by adding them. We can find a sum of multiples of those two vectors. It gives us any vector in this plane. And if we want a different plane, well, orient the board a little differently. v1 and v2, of course, get oriented a little differently. They have to stay in the plane, and they can give you any vector in that plane. Okay, well, in any case, we say then that since any vector in the plane can be expressed as a linear combination of this v1 and v2, that the vectors v1 and v2 span the plane. That's what it means to span a space. Okay, now if we wanted to span three-dimensional space, well, we would have to have two vectors that span some plane. Okay, any of the two vectors would have to span a plane, and the third vector would have to be out of that plane. Then we would have vectors that span three-dimensional space. Now that takes some proof, but that's the case. Okay? Now, we can say then that a plane is a subspace of R3. Now, I'm being a little sloppy with my wording. A plane through the origin is a subspace of R3. Okay? So, any plane through the origin is a subspace of R3. I've got a statement down here that I don't want to pursue right now, come back to it. So what we do is, don't know where I define my plane. Okay, well, we're working off of a worksheet, so I have to say what I'm doing. Okay, so I'm going to come up here, and my premise is that AX plus BY plus CZ equals 0 is a plane through the origin. This is a true statement. And it's also true that any plane through the origin has this form. Okay? Now that's something, we prove, we prove it in multivariable calculus, but it actually can be proved in courses at lower level than that. We could prove it in this course, but we'd have to get a little deeper into the geometry of three-dimensional space than we need to in this course. So right now we're just going to accept this. I'll just say it's easily proven. So we're going to some things wrong. Okay, well, we're going to go on with this idea. We're going to get three equations and three unknowns and test whether we actually have a plane in space and so forth.